In this lesson on synaptic plasticity, we'll look at the components of LTP. There are two phases that scientists have identified, an early phase and a late phase. So you'll recall the scenario. We initially send a test pulse down one pathway and we record the response on the target cell. Then we send a high frequency train of action potentials and then do more test pulses, and we see LTP, a long-lasting potentiation of the synapse. Now, scientists have identified two phases to this phenomenon, an early and a late phase. And the evidence so far indicates that the early phase of LTP is due to local phenomena, local changes at the synapse, whereas the late stage of LTP requires gene activity and protein synthesis. Now, what is the evidence for this story? Well, some of it includes the following kind of experiment. If you cut the dendrites off of the cell body, you can still establish early LTP. So if you stimulate this with high-frequency action potentials, you will get an increase in synaptic efficiency here, but just for a time. Then it will decay. You won't get the late phase of LTP. The LTP will not persist for the 8 hours. So when dendrites are cut from the cell body, early LTP can form, but late LTP cannot. And this suggests that late LTP relies on products made in the nucleus. But now, what would be happening for the early LTP? What's going on locally at the synapse? Well, scientists have gathered evidence that one of the things that happens is that more receptors are inserted into the spine membrane. So here we see a spine coming off of a dendrite down here, and within the spine are vesicles that have receptor proteins in them, and these vesicles can fuse with the membrane of the spine, thus inserting more receptor proteins into the spine membrane. And if you have more receptors, that means there's going to be a greater electrical response in the spine for a given amount of transmitter released. With more receptors here, there are more channels to allow sodium into the spine, generating a larger target cell response. So we're going to think of this as a functional change that can happen relatively rapidly. Here's the synapse before stimulation. Now we're going to induce LTP, send high-frequency action potentials down to the synapse. What happens fairly rapidly is that the spine is going to insert more membranes into insert more receptors into the membrane. In addition, there's evidence that the receptors that are already there get modified so as to increase their conductance. They can allow more sodium into the spine. So the early stage of LTP happens rapidly and seems to involve functional changes localized at the synapse. Well, what about the late stage of LTP? Well, when scientists add drugs that either block protein synthesis or messenger RNA synthesis or gene transcription, what they find is those procedures can block late LTP. So procedures that block messenger RNA or protein synthesis interfere with late LTP. Thus, there's a time window within which early LTP can be converted into late LTP. Initially, there are local events that increase the functional strength of a synapse. That's early LTP. But for late LTP to happen, you have to have these nuclear events. You have to have gene transcription, messenger RNA production, protein synthesis. Now let's take a look at the effect that weak inputs have to the target cell and why they can only make functional changes. Up here at synapse number 1, let's just send one action potential down. We get a very small response. And that would be the red record here. In fact, at such a synapse, you won't see any LTP at all. At synapse 2, we're going to send low-frequency action potentials down here, so you'll get a larger postsynaptic response. You'll only get the early LTP, and then it decays. What is common about these two scenarios is that neither of them are sufficient to bring the target cell to threshold to generate action potentials. So we're only getting early LTP at synapse 2 and no LTP at synapse 1. What's missing here is the activation of the target cell. So it seems like target cell activity is needed in order to trigger those events that lead to late LTP. So in order to get those long-lasting LTP, the late phase of LTP, the long-lasting changes to the synapse, the target cell has to fire, and that seems to be triggering gene activity and the production of proteins. And perhaps these proteins, the hypothesis goes, these proteins that are newly made will be able to strengthen relevant synapses for a longer time. We're going to call these proteins plasticity-related products or plasticity-related proteins, and they're responsible for creating the late phase of LTP. So we can think of the early stage of LTP as a functional change at the synapse, while the late LTP is a structural change, and if you fail to make those structural changes, the LTP will decay. The structural changes require gene activity and protein synthesis, and those proteins then are going to be utilized by the relevant synapses to make long-lasting modifications to the synapse. Here we see again a summary picture. On the left we have the functional changes. We said the increasing the conductance of channels already in the spine, inserting new receptors in the spine. That would be early LTP. And then structural changes, changing the structure of the spine itself, making it wider, having more sites for receptors. Perhaps the presynaptic terminal is enlarged as well, so there's more transmitter release per action potential. These would be structural changes that seem to require protein synthesis. Now, one of the puzzles of LTP early on was, how is it that LTP is specific to the synapses that were activated? So, for example, if we send the high-frequency action potentials down this pathway and we generate late phase LTP here, well, that was the result of plasticity-related proteins. But those proteins should be diffusing all throughout the dendrites. In theory, they would be available to all synapses. So if these proteins go to all the synapses, why aren't all the synapses being strengthened? And one of the ideas we'll see in the final lesson here is that there appears to be a tagging phenomenon. Only those synapses that were recently active are going to be biochemically tagged so that the plasticity-related products will only be able to assist in strengthening those tagged synapses and not others.